get started, just heads up to hold off on seconds just for a little bit. We have intro lab that's still there's people that are stuck, I believe. That's what Max was saying. They're not here yet, so just save some for them. Anyway, so moving on, welcome to the November general meeting. Thank you guys for coming out. It's kind of a big deal to get this kind of turnout this late in the semester because I know that everybody's really, really busy, so I really appreciate you guys' time. So moving on to some announcements. So we did officially reach 100 members. So this is a nice milestone. I mean, we've never had 100 members that I'm aware of. This is the biggest membership we've ever had in our history. Yeah, we've tried to do the research for it, and this is the largest we could find. So this is a huge milestone. I mean, props to you guys for being here and being engaged. So we have a cake in the back. Obviously, if you guys are interested in seconds, go for the cake and ice cream over to the left, or my left, your right. There's a big cake over there for you guys, so yeah, feel free to partake. Moving on, we have officially donated our hurricane relief funds that were raised back in September and October, and had our professors pied and whatnot. So the actual, administrative part of it is now also complete, which we went ahead and we made it we got, all of our officers to vote on it, and officers have voted to donate it to Doctors Without Borders. So they received $2,033.53 from OU Scan and OWL and all of the organizations that were involved in that, and obviously from you guys. So I really appreciate you guys' engagement this semester. It's been awesome. Third thing to note, so we are going to do a time capsule. The AMS National Organization is also doing a time capsule at the annual meeting this year. And so we thought it would be a good idea to do our own chapter time capsule, which we'll be doing in the spring. So be thinking of things, we definitely, something smaller, something that has meaning but smaller, to put in the time capsule for the student chapter, and more information on that will be coming next semester. First tornado contest, you probably are wondering what that is because I haven't passed it out yet, but we, just like the first measurable snow contest, we're also doing a first tornado contest for the spring. Unfortunately, we don't have a winner for the first snow contest yet. We got really, really close back in October. I know that we had a trace measured, but that doesn't technically count. It has to be measurable.
My car windshield.
It's not quite there yet, but yeah, we'll obviously have an announcement on when there's an actual winner for the snow contest. But we went ahead and decided to do the spring tornado contest because we obviously we're not going to see you guys until February. So if there happens to be a rogue tornado that decides to develop in January, obviously the contest would be obsolete. So we want to make sure that this is out to you guys, so you guys have the opportunity to partake in it. So I'm going to pass this around, and would you like to okay. Pass it around and fill it out. So it'll be guessing the first dates of, or guessing the date of the first tornado in Oklahoma. There's some interesting facts on the bottom of it, just to give you kind of some reference of exactly kind of maybe the ballpark to guess in. A tiebreaker is we're going to have you guess the strength of the first tornado. It's anybody's guess basically. But I think for reference, this year's first tornado was in March, I believe. So yeah, was it? You don't know? Yeah, it was in Shattuck. It was Shattuck? Shattuck. It was March, yeah. It was mid-April? Okay. So yeah, reference this year's first tornado in Oklahoma was in April. So yeah, you got kind of a wide range to work off of. But take your best guess and see what you end up getting. But yeah, the winners can choose between, I think it's an umbrella, a NWA bag, and a pet tornado. So get a free pet tornado if you want. So moving on, so this is our last event as voted on by the officers. So this is our last event for SCAN this semester, so we decided to go ahead and plug the next events for OWL. So OWL also has a general meeting on Thursday, and then they also have their social event game night, which they do every year, which is going to be Friday, December 6th, so we wanted to give you guys a shout out. So that's a really cool little thing. We kind of did something similar for the new student mentoring, but basically it's a bigger deal for OWL because they do it every year. So, and then also for anybody that has 100% attendance this semester, we're also having a raffle at the end of the meeting. So we'll be obviously we have your if you checked in, make sure that you're checking in, obviously, because that's something we're going to be able to be entered into the raffle. So if you have 100% attendance this semester, then you'll be able to potentially win your dues back for this semester. So kind of a nice little incentive. So if you're not in the group me, that's the QR code. I'm pretty sure most of you guys are, but you can take a picture if you need to. Otherwise, that's the main announcements. Is there any questions over the announcements? No? Okay. And then this is the spring schedule as proposed currently. So this is some exciting things. This is kind of what we were hinting at in our social media. So it's not firm completely yet on all of these dates, but definitely some really exciting things coming up. We have January 21st is the RU Haulings Help Session, which will be basically the first thing coming back from AMS for some of you in the second week of school. So anybody interested in RU in the Haulings programs, that's a really, really nice thing to engage in, just to be able to know what to expect of the application process. I believe those due dates are pretty close after that point, so it'd be kind of a good way to wrap up and get some last minute things checked. Groundhog Day party, so that's going to be this January 30th, which is a few days before actual Groundhog Day, but that's usually how we do it. But this year we are planning on doing it at O'Connell's, just like we did for the watch party for OU at UCLA. So that'll be nice, and it's basically a tradition every year. School meteorology and all of the students go out and have a good time and celebrate Groundhog Day, which is, yeah. Another exciting thing is the biggest event thus far at that point will be the February 5th Hurricane Forecasting Workshop with OWL. We have currently planned the Hurricane Workshop will be with Dr. Michael Brennan. Dr. Michael Brennan. He's the chief for the Hurricane Forecasting Division at the National Hurricane Center. He'll be Skyping in. He won't be, unfortunately, be able to be here, but he'll be giving a talk on how to forecast hurricanes operationally, and just kind of giving a lot of the methods that go into how they forecast at the National Hurricane Center. And then our next general meeting for SCAN is going to be February 11th. So that'll be our first official SCAN event, only exclusively for next semester. So just stay tuned on those things. We'll obviously keep you up to date, group me and social media, but those are the big things. Is there any questions over those? Any big concerns? It's also worth noting the March general meeting right now we have planned for as a members pick, so you guys will have the opportunity to vote on the topic and the speaker. So kind of exciting and exciting way to engage with the members. So any other concerns or questions? All right, we're going to go ahead and move on, and that will be with our doctoral candidate, Addison Alford. He's with the Smart Radar Research Group. It's under Dr. Michael Biggerstaff, and I will let him take it over from here.
Okay, well, thanks guys for having me out tonight. It's a pleasure to be here. And as a past president of this chapter, it's great to see you guys hit 100 members, so congratulations on that. We never hit such a lofty goal on our membership. I think when I was the chapter president in 2014, when some of you were probably still in middle school, which makes me feel old, we were probably at about 60 or 70 members, so 100 members is a great achievement. Tonight, I'm going to talk to you a little bit about what we do with the Shared Mobile Atmospheric Research and Teaching Radars, and our work in observing hurricanes as they make landfall on the United States coastline, and I'll even throw in a few observations from the Burkett Southeast field campaign that's been happening over the past few years right at the end of the presentation, so you get a little bit of tornadoes just to satisfy your interest. But before I do that, I have to throw in, which is tradition, starting with Dr. Jeff Becerra. In his colloquium a couple of years ago, he created what we call our alternative titles to these talks. So my first alternative title is descriptions of spinning things that aren't tornadoes. Yes, they do exist, people. Tornadoes aren't everything, even though it seems like they are here in Oklahoma. I'm not encouraging you to go hurricane chasing, though. In fact, I'm discouraging that. Please do not do it. And the other alternative title that I have, if you don't know me, I tend to drink a lot of coffee, but in order for me to endure a hurricane, lots of coffee is required in order to do these deployments. So who am I? For those of you that don't know me, probably basically everyone in this room, I feel disconnected a lot. Even though we're both students in the same program, I rarely see you guys. I'm from a small town called Somerville, Tennessee, right outside of Memphis, Tennessee. And as a high schooler, prospective student here at OU, I knew I was very interested in tornadoes and math and science, probably many stories like you guys have in here as well. So I chose OU as my home, and that became my home for my bachelor's, master's, and now PhD, where I've been in the School of Meteorology since 2010. And given my childhood love of math and science, and of course tornadoes, I found that it was a great way to apply those interests here in the School of Meteorology and as a career. And but that wasn't really everything that I enjoyed. I really like being an active participant in research projects. So I've joined the Smart Radar team back in 2012. There's a photo of our group before the pecan field experiment. I was myself and Mr. Gordon Carey, you might have seen him around the School of Meteorology before. We were managing the Smart Radar 1, which I actually killed during that particular project. But I joined that team, and I've been doing a lot of field work ever since with the Smart Radars. Again, stand for the Shared Mobile Atmospheric Research and Teaching Radars. So here are a few photos of the Smart Radars, including field projects that I've been involved in. This was from the Deep Convective Cloud and Chemistry experiment, where we were working with both of the radars as well as the NSSL mobile NOXP radar to sample deep convection and its influence on distributing trace gases throughout the atmosphere. The G4, which is a NOAA-operated jet that can fly at about 35,000 feet, was flying around the anvil of the thunderstorms that we were sampling from the ground. And so we were involved in that. So ironically, even though I've gone on to hurricanes and I've been involved in some tornado experiments as well, my first experiment ever was actually a chemistry experiment, which is not often perhaps appreciated in this school, but there's a whole branch of atmospheric chemistry, whether you knew it or not. If you're in Cameron Holmeyer's class, you've probably heard him talk about it. So ask Cameron about that if you're curious. But the radars have been involved in a number of experiments, including lightning experiments, obviously tornado experiments like Vortex 2, Vortex Southeast. This particular experiment was a NASA-based experiment. There's the DC-8 aircraft from That was in Costa Rica. That was before my time. And then hurricane experiments. This is a photo of Gordon and a couple of Mike's past students during a hurricane landfall. So the program has several different objectives. Obviously research, scientific research is our primary objective, but we have some secondary motives as well, including outreach to the general public. There's a photo of the original Smart Radar, Smart Radar in the Norman Christmas Parade one year, just simply doing outreach to the general public. I drove one of the radars in the homecoming parade for the OU homecoming last year, not this year. We also have opportunities to help with K-12 science education, giving students experience, not really experience of running the radar, but at least experience of seeing what a radar is, how you do meteorological research, and giving them an opportunity to witness the radar actually scanning and things like that to kind of excite and pique their interest. And then educational opportunities for you, the university students, undergraduates and graduate students alike. The Smart Radar program, Mike, my boss, is particularly interested in getting undergraduate students involved in research early on in his group. And he usually has a couple of opportunities every year for editing data and participation in field programs. So if you're interested in something like that, now or in the future, whenever his door is open, you're always welcome to go in there. Even if you don't know him, just tell him Addison sent you, and he'll believe you. We currently have 2 radars in the program. SR2 is the older of the 2 radars. It has all the logos on it, so if you ever see it driving around campus, you'll notice SR2. This is a photo of it deployed. I don't even know where this is Mike's photo. This is the older of the 2. It was upgraded to dual polarimetric technology in 2009 and 2010 for use in the Vortex 2 field campaign. And the pedestal was brand new as well. So basically all the components on the back of the radar were all brand new for the Vortex 2 field campaign. SR3 was completed in 2017 when I broke the original SR1. In 2015, it took about 2 years for us to rebuild it, thanks to the National Severe Storms Lab. And its first deployment was in the Vortex Southeast field campaign, where Mike was operating that radar. And so there's Mike getting in before its first drive out of the vehicle bay here at the Weather Center. And it's very similar to how this one is designed, except the antenna, the dish on the back of SR2 weighs about 700 pounds. The new one is a nice light composite material weighing only about 150 pounds. We are actually worried about taking that one into a hurricane environment because being a lighter dish, we were wondering if the strong winds and a hurricane would actually warp the dish during big gusts or something like that. But luckily, that seems to not be the case. So it's a pretty well-built dish. My particular involvement in the SR field campaign has ranged from the DC-3 field campaign that I told you about to lightning work with DARPA. You might know them more as Department of Defense experimental aircraft designers and weapons designers, but they actually had interest many years ago with us to do lightning research. So we did that in Florida, so that was my second field campaign. There I am on the back of SR2. Then the Pecan field experiment, which was the planes elevated convection at night experiment. We were studying nocturnal thunderstorms all across the Great Plains and literally living at night. We slept during the day and had to get up at night. Then Vortex Southeast, these bottom 2 photos with SR2 in front of the NOP3, which was involved in a number of years of that campaign. Excuse me. We've been involved in that as well in recent years. So in total, ever since my beginning in the SR program, I've totaled 41.5 weeks in the field. I do keep track because I'm trying to beat Dan Betton. He was a PhD candidate and now has moved on to a job in the private meteorological world. He has a total of 52 weeks in the field, so I'm trying to beat Dan as being the record holder, besides Mike, of course. Mike's probably been in the field for like 200 weeks, maybe 2,000 weeks over his career, but I'm trying to beat Dan Benton, so it's just kind of a personal thing for me. So getting to hurricanes specifically, the radars have been involved since 2001. It was actually their first deployment into Tropical Storm Gabrielle, a landfall on the southern Florida peninsula. So that was a NASA-sponsored field program, and ever since 2001, the radars have observed, I think, 13 total hurricanes at landfall, most of which, about half of which, have come since 2016, including Hermine and Matthew in 2016, Harvey and Irma in 2017, both very famous storms. You probably are well aware of why. And then 2018, we sampled Hurricane Florence, and just this past August and September, we sampled Hurricane Dorian. So a good number of hurricanes in the past few years, which totals to approximately 14,315 highway miles, not including all the miles that we have to drive around to scout sites for the radars and just go back and forth between dinner and our hotels. But 14,000 plus miles, which on Google accounts for 189 hours of driving time, but these trucks are pretty slow, so let's add another 10 to 20 hours, so upwards of 200 hours total on the road for me since 2016, just in the radars. And then that equates to, by a very rigorous algorithm that I've developed, approximately 400 cups of coffee consumed by me alone during those deployments. You think I'm kidding. So what do we do? Why are we doing these deployments, especially here in Oklahoma? So there are a couple of traditional methods of observations of tropical cyclones, most of which are over the open ocean. For example, the NOAA P3 routinely flies into mature and developing tropical cyclones out over the open ocean, if they're close enough to an airport from which the P3 can take off. And they make these passes through the center of circulation. So this is a figure from Rob Rogers, who works for the Hurricane Research Division. This pass one would be this data right here. That's all you would get because they're using a very short wavelength radar on the P3 in order to retrieve the wind field. And so you can't see very far in the precipitation of a hurricane using this radar. So you only get these kind of radial-oriented snapshots outside the eye wall, in the eye wall, which is right here, and then through the eye. So in order to get a better picture of what's going on completely around the eye wall, what you need to do is actually take another pass to get another component of the eye wall, and then do a third pass as well, in some cases, to get the final bit of data to get a good wind retrieval for a hurricane. But and all of these data are collected with various goals in mind, depending on the year and what the active area of research is for the Hurricane Research Division and the Hurricane Hunters. But a couple of things that they've really targeted lately are tropical cyclone development, rapid intensification, and rapid weakening. The weakening component is particularly difficult to forecast, more so possibly than even rapid intensification. And then intensity forecasting. That's lagging very much behind our ability to forecast the track, which heavily relies on the synoptics of the atmosphere rather than the convection surrounding the eye wall that leads to the intensification of a mature tropical cyclone. The weakness of using the P3, not to ding the work that HRD and others do, but you only get snapshots of convective processes that are really important to understanding why a tropical cyclone is going to rapidly intensify or rapidly weaken. And then landfall is difficult to observe sheerly for the fact that the P3 does not fly over land during hurricanes. It will not fly over land, and that's because turbulence rapidly increases in the lowest part of the atmosphere. It's very dangerous for the aircraft to fly over land during hurricane landfalls. So you cannot really get much data out of the land, even if the P3 is flying basically parallel along the coast. It's really difficult to get data. So that's where we come in. We've used the smart radars and collaborated with the National Severe Storms Laboratory using mobile mesonet and sounding units over the past 3 to 4 years to examine convective processes that can lead to intensification, the rainfall and wind distribution at landfall, and dynamic processes that are active during landfall that might be applicable to over open ocean observations. We can collect observations in a much more continuous temporal framework than over a much larger area than can the P3, for example. So we can look at things like these mesovortices that are rotating around the eye wall of Hurricane Harvey during its landfall. These don't just happen during landfall, they happen out over the open ocean. But the P3 can only generate basically a snapshot of one of these at a particular time, whereas we can take observations continuously in time and try to understand why they exist and what influences they have on the intensity of the tropical cyclone. But our weaknesses lie in the fact that we can't take over ocean observations. There's no smart radar boat or anything like that. And then we have to account for friction. There's increased friction on the land surface compared to the ocean, which disrupts the circulation, and that's actually why hurricanes spin down at landfall, is because the pressure gradient is being disrupted, so the hurricane fills in. So our goal as a more cohesive unit in the science community is to utilize the strengths of the airborne and over water and ground-based data sets to understand dynamic processes that lead to intensification, wind distributions, and precipitation processes, both over the open ocean and at landfall. So I'm going to briefly show you some of the science that we're working on. This is Hurricane Harvey, so this is one of our best cases ever sampled by the smart radars. We were located literally just inland of the Outer Banks of Texas. Corpus Christi, for reference, is about right there. And a few notable places that you might have heard of, Port Aransas, which was devastated by Harvey as it was making landfall, is about right there. Rockport and Fulton are right there on that little peninsula. So we were a little bit farther inland than that in order to make sure that we could continuously operate in the extreme winds that Harvey had during its landfall. At closest we got to the eye wall, it was about 5 miles or so outside of the eye wall. And the winds were only about Cat 1, maybe verging on Cat 2, but in the eye wall they were Cat 3 or Cat 4 at landfall. So that just shows you how strong of a gradient in the eye wall that the winds had. It was a very long deployment for us. If you look at the left photo of me being interviewed by actually another SCAN alumnus, Megan McClellan. She works at Tulsa now, in Tulsa as a reporter and a broadcast meteorologist. She was interviewing me, and that's a very confused photo because I remember actually doing that interview after being up for over 24 hours straight, and I couldn't think at that point. So she was asking me a question, and I remember having to sit there and think about what she literally had just asked me. It took me like 10 seconds to respond, to get a response going. And then later I was talking to Mike. They took a shot of me and Mike just talking, and you can see Mike's confusion at one of the responses I'm giving him at that point as well. So again, being up for 24 hours plus, I really don't recommend it, especially when you're having to think about science and staying safe and things like that. So all jokes aside, Harvey is a great case for us because those mesovortices that I mentioned in the earlier animation, this is the same animation as again. So these mesovortices are asymmetries in Harvey's eye. They were particularly manifested after 2 UTC on the 26th of August, 2017. And they were propagating against the mean wind, which is consistent with what's called vortex velocity wave theory, and I'm not even going to get into that, except to simply just mention it. If you're ever interested in that, please come to one of my seminars in the graduate program, and maybe you'll learn a little bit more about that. But what's important is these asymmetries are really, really important in exchanging momentum and for those maybe in the senior capstone or in an upper course in dynamics, exchanging high potential vorticity between the eye and the eye wall. So basically what that means is these mesvortices are not just they're not just in the flow rotating around, they're actually exchanging momentum from different places relative to the center of circulation, at least from the data that we've collected. And this is an active area of my PhD work. This is an active area of research in general in the tropical cyclone community, but it's one that is very difficult to observe in a high temporal framework, yet with observations like this, we're able to do that. And so what can be said about their effects on the landfall process? So on the left figure, you have a wind map, maximum wind map of all of our data. So how you read this is given all of our data from 2050 at UTC on the 25th of August through 26 August at almost 6 UTC. We take all of our analyses of the two-dimensional wind field at 500 meters above the Earth's surface, and we say at each grid point, what was the maximum wind experienced at that grid point? The figure down here is very similar, except it's just telling you what time that maximum wind occurred on this map. So what you can see from this is one, you get this nice swath of 60 plus meter per second winds at 500 meters, not at the surface, but at 500 meters. So basically you can see the translation of the eye as it's, the eye walls as it's moving on shore. But what you see amongst this otherwise kind of homogeneous path are these perturbations to the background maximum wind, where you're getting maximum wind speeds upwards of 70 or even 80 meters per second at 500 meters. So, and these are kind of azimuthally oriented, meaning they've kind of translated with the eye wall, with the strong flow of the eye wall. So we immediately thought it's got to be, they've got to be associated with the mesvortices that I showed in the previous animation. But this is at 500 meters. What does that say about the surface specifically? And that's where our observations and the observations of the National Severe Storms Lab come in. So, oops, sorry guys. We have the smart radar, and we're combining our data with, in the case of Harvey, we were combining it with the 88D to retrieve the full three-dimensional wind field during the landfall process. But NSSL, Dr. Sean Waugh at NSSL, begrudgingly perhaps, because I kind of pushed everyone out the door for this particular landfall mission, he said, why don't we start launching soundings during the landfall process? And I said, you're crazy. How are you going to hold onto a 5-foot balloon in a Cat 3 or Cat 4 hurricane at landfall? There's no way. But Sean came nonetheless and began launching soundings for us from a ground-based perspective, which rarely happens in a landfalling hurricane, again, because you have a 5 to 6 foot balloon and you have hurricane force winds. It's really hard to hold onto the balloon. So we've been collaborating with Sean. We've collaborated with NSSL for many, many years, collaborating with them using the mobile mesnets and their sounding capabilities, but all in environments in which it's fairly easy to operate relative to a hurricane environment. So Sean was instrumental in figuring out how in the world to launch these soundings in a really strong wind environment. This is one of the results. So, and I'll show you a video of those soundings being launched here in just a second. So this was a sounding that I actually helped him launch. We drove from the radar's position into the eye wall and just on the interior edge of the eye of Hurricane Harvey. This is a 3D rendering of radar reflectivity, and that little white line there is the trajectory through space that the sounding took as it traversed the interior edge of Harvey's eye. If you're on Twitter and you were active during that event, you probably saw this sounding get retweeted several hundred times, because as soon as Sean posted it, it got a lot of retweets, mainly for this particular image right here, this photograph. So let me ask you, if you saw this photograph here in Oklahoma, would you be running out the door and skipping class? Be digging a bunker? I actually would too. So, what does this photograph tell you? Those of you that have dealt with the sounding so far, what does this photograph tell you? Do what? Yeah? So that photograph should not actually be read as a traditional photograph. What do you assume when you plot a photograph of a sounding? Yeah, it goes straight up. Yeah, that's what you assume. That particular photograph right there actually shows you more of a trajectory than it does what you're looking at when we assume that a sounding launched from, like here at the National Weather Center, we assume it goes straight up. It's not really true, but we assume it to be fairly representative. So one, that photograph is not representative, meaning that in hurricane flow, soundings in this particular region are all but useless as far as examining a point profile of the vertical structure of the winds, unless you assume that the winds are completely homogeneous around, which I just showed you, which was not the case from our Doppler analysis results. The second notable observation from this is the observation of 3.26 inches of precipitable water. And that, from what we can tell, is likely a continental United States record from a ground-based sounding. So Sean is still looking into that, but we're pretty sure it's probably going to hold in the end. So that means there are 3.26 inches of water available to fall in that part of the atmosphere that the sounding was actually able to traverse to rain out on the Earth's surface. And just for reference, for those of you who may be unfamiliar with PW values, a good flooding event here in central Oklahoma, 2.6, 2.7 inches maybe, and that's like a 95th percentile PW value probably. So really, really high values of precipitable water. So what does it look like to actually launch one of these soundings? What you're going to see is we're actually positioned behind the mobile mesonet, which is pointing into the wind at this point. So we're using the back of the truck to basically be a shield. If any of you have seen these launch tubes, all this yellow tarp is the launch tube that's holding the balloon. Sean had to lay in it in order to keep it from blowing away. So he's laying on the road surface basically. And there I pull the strap off, and then Sean pops out like a jack-o'-lantern, and away the balloon goes. This was in the outer bands of Hurricane Irma. But getting back to Harvey, all the difficulties aside in launching these particular balloons, when we were launching in the outer bands and the outer edge of what's called the inner core, the general stratiform type rain region surrounding the eye, we were able to retrieve the lowest part of the atmosphere in terms of its boundary layer profile. So these are some of the observations. You can see it's a quasi-linear profile in the lowest part of the atmosphere, which is what we can use then to take that wind map that I was showing you, this wind map at 500 meters, take the spatial distribution of the aerodynamic surface roughness. If you've not heard of this term yet, it's perfectly fine. But you're accounting for the surface characteristics that would cause friction to be felt by the atmosphere above the surface. And you can take the observation of this maximum wind, take the surface characteristics, and then convert this 500 meter wind to a 10 meter standard wind at 10 meters above the Earth's surface. And so then what you see are these two top figures are before landfall, and these figures are during and after landfall. What you see is the general homogeneous eye wall, maybe some relative perturbations in the maximum wind field at 10 meters. And then particularly at landfall, you see these associated with the swaths that were aloft, the 500-meter swaths. You actually see perturbations along the coastline within about 5 kilometers, exceeding the Category 3 criteria for wind. And that's the only point in this 10-meter wind field that exceeded Cat 3 winds, with the exception of the surfaces over the open ocean. So to make that a little more clear, the strongest winds in a hurricane are only going to be felt within about 5 kilometers of the coastline because of the influence of the land surface on a hurricane, which might be why many people have questioned in the past 5 to 10 years, why when you have like a Cat 5, like Hurricane Michael, why is it so difficult to find that Cat 5 observation of winds on land? Well, most ASOS stations aren't right on the coastline. Most of them are 5, 10 kilometers in from the coastline, and they only experience Cat 3, Cat 4 winds. These observations are very important for us to understand the spatial distribution of the wind field during the landfall process. And we were able to validate this method of projecting the winds using those soundings, as well as collaboration with the Texas Tech University StickNet program, who had anemometers all over this area. So we were able to validate that maximum wind that we observed and the projection from 500 meters to 10 meters. Now, we need to extend these observations over to the open ocean in order to understand if these same types of dynamic processes are ongoing in there out over the open ocean. So what I propose to do is get a yacht and put a smart radar on the back, and then we can do whatever we want, basically. It seems pretty reasonable to me. However, Mike said, Addison, funding. I don't have funding for, I can barely get away with sustaining the Smart Radar program with, NSF grants. How am I supposed to buy a $100 million yacht? I still think it's possible. But there are other ways, other $100 million ways to take observations of hurricanes out over the open ocean. For example, HIRAP. HIRAP is a radar system that is placed on the bottom of the Global Hawk, the NASA Global Hawk. This is the drone. It's an old military drone. But what HIRAP does is it takes conical sweeps below the aircraft and sweeps out these conical surfaces, taking an observation from offset antennas on the bottom of the aircraft at 30 degrees and 40 degrees off the perpendicular to the aircraft track, so off nadir. And so by taking these conical surfaces, you're sampling all the points below the aircraft, both on the forward pass and on the aft pass. And you're sampling them 4 times because you've got 2 beams that are hitting each point on the forward pass and the aft pass. And for each of those beams, there are actually 2 frequencies that are collecting data. So actually you get 8 total observations. So this can be used to perform 3-dimensional wind retrievals in cases like Hurricane Matthew, which is another hurricane that we sampled. So the Global Hawk took this nice look across the Hurricane Matthew circulation as it was passing by the Florida coastline. And what we're interested in are not only the dynamics associated with the eye wall, but these rain band structures here out just beyond the eye wall. This is the eye here, and these deep convective rain band structures, which are not supposed to be there according to most conceptual models of hurricanes. We want to know why they exist, and that's particularly tied to observations that we've collected at landfall. So just to show you these rain band structures, they do exist outside of the eye wall. You only get a very limited window in which to view them, but they're useful nonetheless. And they seem to be associated with deep tropospheric waves that are propagating outward away from the eye wall. That vortex-Rossby wave thing that I mentioned earlier in the talk, these deep tropospheric waves are induced dynamically from perturbations within the eye wall, aka mesovortices. And so this whole process likely leads to rain band formation, not only out over the open ocean, but at landfall as well. So that science aside, excuse me, we've also sampled other hurricanes besides Harvey and Matthew that I just showed. Florence was one such case where a group of 5 of us, Sean, we've now gotten him hooked on doing soundings in hurricanes, so I don't really have to convince him to go with us anymore. It's like a drug to him, I think. But Sean is more than happy to go with us, and we wrangled Noah Brower, another grad student in the program, to go with us out to Florence. And we had these instruments called the PIPs. They're portable integrated precipitation systems, or again, PIPs. They're distrometers, laser distrometers. If you don't know what that is, that's perfectly fine. It's simply a laser instrument that is designed to sample the number and the sizes of raindrops as they fall through the opening at the top of the instrument. In this particular case, OU, the OU Nightly folks kindly featured us. We do have live cameras in the truck that actually stream to the Weather Channel. But in putting those, they're just Nest cameras like you'd have for home security. In putting those Nest cameras within the trucks, which were active in Hurricane Harvey, but maybe not as popular as they were during Hurricane Florence. You're able to actually watch us in real time, and anytime the Weather Channel takes those feeds, luckily they can show what real meteorology, what real research is like. It's not all glamour like in Twister. I mean, we don't see an F1, F2, F3, F4, and F5 tornadoes sequentially over a day or two time frame and send magic sensors into the sky and magically understand what tornadoes and hurricanes are doing. It's more me sitting there, hopefully not doing anything or saying anything too embarrassing. But then you can, Weather Channel and of course OU Nightly can take that feed and show folks what we're actually doing out in the field. To give you perspective of what it's like to drive into a hurricane disaster zone, which is a really eerie feeling, especially post-Harvey and post-Irma. This was us driving into Hurricane Florence, which was SR3's, the radar there. The newest smart radar, that was its first deployment. And as I probably don't have to describe, you can see the entirety almost of Wilmington, North Carolina evacuating on the interstate, as we are basically the only vehicle going into these areas, with the exception of trucks from like the Weather Channel and emergency response units that are positioning ahead of the disaster zone. Wilmington was a particularly devastating event. I probably don't have to tell you. There was immense flooding in that area associated with the landfall and slowing of Hurricane Florence, and actually trapped us for a number of days. We just couldn't drive out. It was very difficult to get out because almost every road into and out of Wilmington, North Carolina was completely inundated with at least 3 to 5 feet of water. So it was literally on an island that did not exist before. Luckily, about 2 days into us being trapped, we were able to get out and get all the vehicles out and get them to safety. Not that they were in any danger before. They were on very high ground, and they were locked up and everything. So we just sat there and had food and maybe a beverage or two. During the landfall of Hurricane Florence, before we actually got trapped, what did we do scientifically? Well, in Hurricane Harvey, we had 7 stick nets that were placed around the area of Harvey's landfall by John Schroeder et al. At Texas Tech University, giving us 7 verification points for this method of retrieving the 10-meter wind field from our dual Doppler analysis results. But during the landfall of Hurricane Florence, we coordinated with John and his colleague Brian Hirth, who were coordinating their part of the mission. And all of these dots across the Wilmington, North Carolina, and inland area, all of these dots represent a location of one of those stick nets, and that doesn't even count the other stations, the other PIPs that we placed around the area, which have sonic anemometers on them as well. So we have 4 additional of those, and so in total we had like 25 to 30 validation points around this area. We're actually a pretty large spatial area in order to work on this method of wind retrieval and validate it further. So this is kind of what we got. Excuse me, I'm getting over a cough. This is kind of what we got. So as Florence kind of moved from east to west, and then began taking a dive to the southwest as it skirted past Wilmington, North Carolina, briefly making landfall in that area. The winds aloft at, I'm showing 1,500 meters here, they exceeded 70 meters per second at one point, but quickly depleted through time as the hurricane was interacting with increased shear during landfall. And so the spatial wind map across the Wilmington area aloft is only 40 to 50 meters per second at that level. So the strongest winds were definitely experienced out over the open ocean, but given that we have all the stick nets across the area, our pips as well, this gives a great opportunity for us to validate this retrieval method. Now, Hurricane Dorian, I'm almost finished. I'm going to wrap up here in just a few minutes. Hurricane Dorian, we yet again collaborated with Texas Tech University, kind of by chance. We stayed at the same hotel that they did in Orlando, Florida. Those are the KA band radars operated by Texas Tech there, and then both smart radars there. Dorian was a bit of a frustrating deployment for us, even though it went really well. We had dual Doppler lobes, meaning areas over which we can perform three-dimensional wind retrievals over Cape Canaveral, the Space Coast of Florida, on down to where I was operating SR2 south of Melbourne, Florida, and well north of the Miami, Fort Lauderdale metro. It was frustrating because the hurricane stayed well offshore, but nonetheless we were able to prove a concept that we've been working on in the group using our OU, AT&T, and Weather Channel partnership. AT&T provides the data for us to actually be able to stream those Nest cameras in real time to the Weather Channel and on the live feeds that you guys can watch. The AT&T part of that collaborative effort is what is really vital to us at this point, because we can actually stream all of our data back here to the National Weather Center Smart Radar server and begin processing that data. So the first thing that Gordon Carey has devised is a way to put our reflectivity and radial velocity data on Google Maps, and then we can distribute that link to operational folks like at the National Hurricane Center or a local National Weather Service office in our area. My part in our real-time efforts in order to take our data that we're collecting for research purposes is to actually create two-dimensional wind fields, so the horizontal wind field in real time. When you're taking radar observations and looking at Doppler velocities, you're only looking at one component of the flow. By taking two radar observations at any given point in space, you can then retrieve the two- and three-dimensional components of the flow. So by positioning ourselves in Smart Radar 2, south of the Melbourne WSR 88D on the Florida Space Coast, combine those two data sets as we would in a research dual Doppler analysis framework, but did it in real time. So I basically made some assumptions and bypassed a couple of important steps. But we can retrieve with relative accuracy the two-dimensional wind field aloft. So how that works is we get our data pushed back and we check for current data within the last 30 minutes. The radial velocity data, which we collect in a very raw format, something that you probably wouldn't be used to looking at if you're looking at like a supercell that's producing a tornado here in Oklahoma, where all the data are already de-aliased. We collect that in a very raw format. So we have to use programs like the PyArt, the Python ARM Radar Toolkit, to de-alias that data and remove all the noise in the data. And then we interpolate that data to a Cartesian grid, combine that data set in dual Doppler analysis to retrieve only the two-dimensional components of the horizontal flow. While that starts, which this process takes a couple of minutes, you go back in a parallel processing framework and start the next dual Doppler analysis. So this happens every about 5 minutes or so, depending on how we're running the radars. So once that dual Doppler analysis finishes up, you're basically ready to pass in the next dual Doppler data set, and then begin dual Doppler, and then begin the next dual Doppler analysis, doing all the editing and the interpolation steps. In between those steps as well, you make plots, and we send them to a web server and send those things out in real time. So we have about a 3 to 10 minute latency period, depending on the bandwidth of our AT&T routers that we have in the trucks. That's only for the dual Doppler analysis, the two-dimensional wind map portion of that. For the just radial velocity and reflectivity images, that takes about 1 to 3 minutes or so before that data or those data are live on our website. A few potential problems that we've had that were augmented by our observations in Dorian. The de-aliasing scheme can be very problematic in Pirate, so we're working to improve that. As well as bandwidth dropouts at various points. If you don't have bandwidth, there's just nothing we can do. So this is an example of our dual Doppler analyses, all of those that were actually conducted from the truck in real time and sent to a web server at OU, where you guys, if you'd seen the link on our Twitter page or my personal Twitter page, you'd have seen these data in real time. So on the left side, you've got reflectivity and wind vectors overlaid at a kilometer and a half above the Earth's surface. Then on the right, you have the magnitude of the horizontal wind. You can see a few fluctuations in that horizontal wind, and those are those de-aliasing problems that we've had, which I'm trying to improve now. So, briefly, as I wrap up, back to smaller spinny things that the smart radars have sampled over the past few years. So, like I said at the beginning of the talk, we've been involved in the Vortex Southeast field campaign. This is an example of a line of convective storms that was making its way towards our location of Smart Radar 2. I was operating SR2 during that field campaign. And this was actually a deployment particularly frustrated me because you see all that mud, well, not mud yet, see all that dirt? Yeah, I got the radar stuck. There's this little rise going to the road, and we didn't think to, put our wheels maybe on the road. So we got stuck in the mud. Gordon and I were just absolutely covered in mud after that deployment. But nonetheless, we have gotten quite a few great data sets from supercell tornadoes in the southeastern United States to what I'll talk about in the next slide, QLCS tornadoes, or these mesovortex tracks in quasi-linear convective systems. So there are a couple here. This is the Doppler velocity field that has been de-aliased. So you see a maximum here, a maximum here, and then a maximum here. Excuse me. This black contour is the area over which we can perform dual Doppler analysis, again retrieving the full three-dimensional flow. You can see appendages in the reflectivity field that's associated with some of these particular maxima in the Doppler velocity, indicating a maximum. These particular areas are indicative of mesovortex tracks. And so, while not attributed often to a loss of life, tornadoes that are produced in these mesovortex tracks in quasi-linear convective systems can definitely lead to immense property damage and as well as injuries. And here's why. So this is a particular event, April 14th, 2018, in Shreveport, Louisiana. Does anyone remember that event? Was anyone on the radar scope for that event? Yeah? What do you remember? Do I?
I just remember the day.
Yeah? Any other memories of the event? Yes, earlier in the day. Yep. But this is the about midnight event from a QLCS that formed in just along the basically I-35 corridor north and south of Dallas. Supercells combined into a line, moved across eastern Texas, and then by by the time it reached us in the Shreveport, Louisiana area, there were multiple mesovortices that were ongoing in this event, and those linear features in the maximum wind field, same thing that I showed you from the hurricane wind fields, but those linear features there that kind of extend across the domain, those are tracks of mesovortices. Those particular wind maxima exceeding 40 meters per second at 500 meters, those tracks are associated with mesovortices. This particular track, I believe just right here, this was kind of what I was trying to get you guys that remember this particular event. This track was associated with the loss of life in an unfortunate circumstance where a house was impacted by a tree that fell from their yard, and unfortunately fell and killed someone sleeping in their bed. So these events, these QLCS events that oftentimes don't, they don't really, they don't end in devastating tornadoes like the May 3rd, 99 tornado in Moore, Oklahoma, or something like that. They're not really super strong or violent tornadoes, but they can indeed lead to the loss of life, unfortunately, through quick tornado genesis events, because that tornado was not actually that long. It was only a couple of miles or so long, the track was. But they can lead to the loss of life through straight line wind events that are associated with these mesovortex tracks, as well as the tornado genesis events that happen along the tracks. So in order to better understand these types of events, these QLCS tornadoes, this data set affords us the ability to retrieve high resolution analyses at even 250 to 500 meter resolution, including this particular mesovortex right here, which was associated with a fairly long-lived for a QLCS track of a tornado in northern Louisiana. This one only did some minor damage to homes, luckily. No loss of life associated with that event. But these events are very important for us to understand, and by using the smart radars, which we were sampling these events at about 2.5 minute temporal frequency, we're able to assess the dynamics that are associated with these events and better understand, and hopefully better understand ways to predict these kinds of events in the future. So, in the interest of time, I'm not even going to read my summary slide. I'll just be glad to take any questions.
So how did you break SR1?
I think we pushed it a little hard during that deployment. No, it was really a hold. It was the original smart radar built in 2001. The gears that actually mechanically turned the antenna, those were the original gears. And it was just, there wasn't much reason to continue to fix it. So Mike knew going in basically that Pecan was going to be Smart Radar 1's last build program. And unfortunately, it was, I think, one of the best cases. Ironically, my fiance works for Conrad Ziegler at the National Severe Storms Lab, and when they were divvying up the cases amongst all the various programs that were involved in Pecan, NSSL, OU, Colorado State University, others, University of Alabama in Huntsville, Rachel told me, I really wanted that case, but it's your fault that I didn't get that case. It was a really great case, but I ruined it, basically. I had to tell Karen Kashiba on the phone that the radar was dead, and it just wasn't going to make it. So we brought it back here, we tried to revive it, but it's time. A little morbid there. Other questions? Yeah?
Do you guys try to place yourselves in the left quadrant when you're deployed on hurricanes, or was that just a coincidence, Harvey?
So there are two ways to answer that. So generally what we do is we try to position ourselves in a very open area where there's going to be absolutely no debris. That mitigates our risk by a lot in a hurricane environment. even high-end tropical storm force winds or low-end Cat 1 winds, they're gonna easily rip roofs off, shingle pieces of shingles or a metal roof, a really wide metal roof. They're gonna peel those roofs right off pretty easily. So we don't want to be anywhere near those kinds of structures. As far as dynamically, we do try to be in the left front quadrant relative to storm motion. Can anyone tell me why? Yes, that is true. But the real reason is relative to storm motion. If you're in the left quadrant, the wind velocities are going to be slightly weaker on that side of the hurricane. Slightly, maybe 5 miles per hour. But that still may be 5 miles per hour that allows us to keep operating. The antenna on those radars, they can only operate up to about Cat 2 sustained winds before they will fail. They're not infinitely strong by any means, and the antenna is basically a sail. So if it catches the wind in the right way or a gust at the right time, it can easily disable the dish. So we try to make sure that we don't get into the strongest part of a hurricane, which would be the right front quadrant relative to storm motion for sustained winds. The other part of that answer, and this is a long-winded answer, but this is kind of a funny story. So the night before, I think it was on the 23rd of August, I was looking at the model data and I said, there's no way we're going to this. Because I had a conference coming up and I was trying to prepare for that. And I didn't want to run down to the Texas coastline for a high-end tropical storm or low-end Cat 1 and then miss my conference. However, the next morning when I got up and realized that Harvey was already a Cat 1 and heading into an environment that basically had no shear and sea surface temperatures of about 30 degrees Celsius, I said, we need to go. But I'd already told Mike that, I don't think this is really worth it. I ran into his office the next day and I said, we're going. And he said, what? He's like, he probably looked at me like, you're the student, I'm the advisor. But I said, we're going. And he looked at me and said, we have a conference. I said, I'll change my flight. This is the data set that we've been waiting for. We need to go. And so I literally, within 3 hours, we were going. We were on the road heading down to Texas. We got there at we got into San Antonio at about 3 or 4 in the morning. Got up at 8 o'clock in the morning. Drove down to set up just off of Rockport, where one of it was, Port Aransas was kind of the landfall point, but Rockport was probably better known as being an area that was devastated during Harvey. So we were about 10 miles inland from Rockport. And during the process of Mike and I driving around trying to find a site, those clear sites that we don't have any debris or anything in our way, the upgrade to Cat 4 occurred. And I was the passenger at that point. And I said, hey Mike, I just got upgraded to Cat 4. And he looked at me and he was like, we have to go inland. I'm like, no. He's like, yes. I'm like, no. If you want the data set that we've really been targeting, then we have to get closer. So the closest he would go was where we ultimately set up. And he did, in some ways, kind of regret that decision. In other ways, we were very safe. We were never in danger. But the winds were getting really strong at one point as the eyewall passed by our location. And so he got worried at one point that we'd lose antenna control. Luckily, we did not. But we put ourselves in an environment that was basically at the top of the range that we could possibly go to. So we learned from that, and I learned that if Mike says no, we should probably not do it. But I pushed him, and that's like the only one that I'm ever going to get. But I pushed him to go get that data set, and luckily it paid off. But we've learned a lot from that experience, including Hurricane Irma later, which for us was not a significant wind event, but it was just frustrating because the radar was basically broken the whole time we were down there. We were operating for 20 minutes, it would fail, and we were off for 20 minutes. So Mike and I just traded off operating that radar every 20 minutes. So that was more of a check your equipment before you go thing. But we just got back from Harvey and we were tired. So, and I did go to my conference. So, any other questions? Okay. Sorry. What's the gas mileage on the smart radars? Well, it depends on if we have a tailwind or a headwind. Headwind, I don't know, 3. Tailwind, that's pretty good, 6 or 7. Good question. Other questions?
What's the tank size?
100 gallons. I don't think on the way to Dorian, I don't think I ever filled up more than like 45 gallons. We stop pretty often, make sure the tank's full. And it's just really hard to drive those things, so you need a break. Boy. We go in the truck base, the truck diesel base, yeah. We get a lot of questions. In areas in central and western Oklahoma, here in the Great Plains, people always point and be like, I know what that is. When you get towards the southeastern United States, you go into Florida, they're like, what is that? And they really look questioningly at the mobile VetsNet. They have no idea what it was. My favorite thing I was ever told was we were in Memphis and we got asked if we were broadcasting the game. That was a fun conversation. Thank you, guys.
Thank you guys so much for coming out. If you guys would pass all of your contest forms to your left, Max is gonna just stand at the end of the road and collect them. If there's any other questions, feel free to come to me after the meeting. But yeah, thank you guys so much for coming out and making history for our student chapter, and I look forward to seeing you guys next semester. If you've only paid for the fall semester, we'll be obviously collecting dues in the spring as well. So last thing before you guys leave as well, we have the raffle. Just so you guys don't head out yet, just for a second. But we have our names of all the people that have 100% attendance. We're gonna do a random generator. And go ahead. Go ahead. It's Tyler Perdon.
Oh.
He won.
Yeah, right.
So obviously we'll do this again next semester as well. So you guys obviously have another chance to win. So.
Okay, I gotta go to Pi 5.
So yeah. Anyway, thank you guys for coming out, and have a good rest of your semester.